substances and solutions, we start to look at the learning goals. We have 3 separate sections. I'd like to make it further through the first 2, although the second one I have to come back to and finish up Thursday, giving section 2 and 3 for Thursday as well. So dabbling in the second, but really solidifying it Thursday. I look at this and say it's a shorter content unit with just 3 sections from the chapter. That's a manageable amount, but because it's heavy in math, it just takes a repetition to become proficient and speedy for test day. So we want to work on both. We'll introduce the chapter by looking at something called formula mass. I call it molar mass, and the chemical unit called the mole. The central calculation of all of chemistry is the mole unit. Once we get a handle on traveling the mole map, the 3 different ways that we measure matter, by weighing it, by taking a volume, or by counting particles, traveling the different roads on the mole map, we move to the next section where we determine empirical and molecular formulas given some mass percentages. So if I know a compound's mass percent, the elements and their contribution to the weight, we can use that information to determine its chemical formula. And the last section is called molarity, which is the concentration of a solution. I'm letting you know that out of the section 3, when you go to read your chapter, there are other concentration units discussed, such as parts per million, parts per billion, percent by mass. I'm taking that off the table and just focusing on the molarity in that particular section. So if you're using those Google slide decks to prepare for each section, you'll see that note made when you get to that. It says focus on molarity, but let the end of that section go. So out of those 3 things, we're going to begin by exploring the mole map. This visual that I gave you as a test-taking tool page, like if you're like me in the visual, it helps me figure out how many steps are involved for each and every calculation I'm asked to make. I consider this a test-taking tool page. You need a periodic table, and if I may, look at the beautiful notes that are on this periodic table that we made together. It had to be virtual because you listened to this, and I see that the charges are placed in each column. I like that. In each box, you place the charges. You highlighted where the metals and nonmetals are. You might have even labeled where the alkali, alkaliners, all of those family. So that periodic table lesson, that's a test-taking tool page. The other, unless you want to memorize them, I would highly recommend that polyatomic ion chart. I gave you a couple of varieties to print out. One of them looks like a long list. The other is in this kind of a boxed kind of chart area. And of course, they're just the best friend to have right in front of me here. The mole map looks like this, and that's the other tool for this particular section. With those tools and a calculator, we're about to engage in the practices of measuring matter and relating it to that central calculation of the mole. What do we remember about the chemical mole from being alive so far in our journey called life? In a different chemistry class, if you've had a background, do you remember hearing the word mole? Let's kind of engage in a conversation with people nearby so I can eavesdrop, so I can hear a little bit of prior knowledge. It's not a question that's right or wrong. It's what do you remember? Have you ever heard? What brings to your mind when you hear the chemical mole? Talk to your neighbor. Anything at all? Pardon? Okay. Is that the feeling here too? What's interesting, and I only made it down the center aisle, but I remember hearing, okay, I printed it, and that's as much as I know. That's a good start. Or some people said, well, I remember hearing it maybe from high school, but it's been a while. We're assuming that, and this is, what they say about assume, but I'm assuming that we have no prior knowledge, so it's all brand new. We're going to introduce the chemical concept of mole as the central calculation of all of chemistry and how we relate it to measuring matter. When we measure matter, we do so one of 3 ways. We can count it, we can weigh it, or we can take its volume. All of the ways that we measure matter, by counting, by weighing, or taking a volume, lead back to the central calculation, the unit called the mole. And it's a standard international unit, MOLE, if you remember on your SI chart from Chapter 1, standard international unit. It's the international unit that measures the amount of stuff. That's literally its definition. The amount of stuff is measured in a mole. So when we kind of think about the mole concept, it's a way of counting by weighing. It's a way of knowing a volume by counting. It allows me to exchange from one measurement to another, which is an important thing in chemistry. I mean, if I think about it, where chemistry actually occurs is at an individual molecular level. And yet it's the most impossible thing to do in a lab is to count out individual particles. 1 atom of carbon, 2 atoms of carbon. We can't do that. And yet that's where the chemical reactions take place. But if I can weigh out the carbon, walk to the scale and weigh out 12 grams of carbon. So you got a big lump of black powder on your scale that's carbon. I now know by knowing its mass how many atoms are sitting on there. The mole is that unit that allows us to exchange between measurements. Chemistry is a very quantitative science. Chemistry can be a very qualitative science. Let's make sure we understand the difference. If it's quantitative, which this chapter is quantitative, it's all about numbers, isn't it? Quantities, number crunching, me and my calculator becoming new best friends. A quantitative lab. Well, you had one, your very first lab. Wasn't that a very calculator-heavy lab where measurements mattered? Your density lab. You had to take great care in getting a precise mass and a precise volume, and those measurements mattered. That was a very quantitative lab. This week, it's more qualitative. Qualitative means, looky, what do you see, right? Observation-based. Describe the texture, describe the color, describe an odor. All of those things that are easily observable about a sample of matter. Qualitative analysis helps me figure out the identities of unknowns, for example. Is this sample behaving the same way as the known? Qualitative example. So in this chapter, we're making sure that we're getting a handle that it's quantitative, number crunching, me and my calculator, as we discuss the chemical concept of the mole. The mole is the central unit that allows me to exchange between the ways that we measure matter, counting, weighing, and taking a volume. So when we think about answers given to us with numbers, quantitative. If we think about answers that are not in numerical form, but rather a description, observation-based, we know that that's qualitative analysis. In chemistry, you will have your share of both. The mole map allows us to measure matter through a central unit known as the mole. When we measure matter, there's 3 ways to do so. We can count it, we can weigh it, and we can take a volume. And on this slide, I simply showed some common ways. Walk down the grocery store aisle and you'll see 3 ways that we can purchase products. You can count out individual particles like apples, eggs, or donuts. I buy 4 apples. Anything more, and I just can't eat them, so they go to waste. 4, that's my commitment. Not 5, not 3, I can get 4. That's counting out. Weighing, you spend time in the bulk food aisle. You can weigh out a certain amount of, I do that for my dogs for milk bones, for instance. Or you buy a pound of hamburger. You're weighing out a certain amount of product. Or you can buy something that's taking a volume, a gallon of milk, bottle of pop, whatever it might be. You're taking a certain volume. In chemistry, most likely volumes are for gases, sometimes for liquids. You can calculate a volume by water displacement for a solid. Notice that by counting, by weighing, by taking a volume, the ways that we measure matter, the mole is a unit that allows me to exchange from one into the other. So if I walk to the scale and weigh something, I know how many atoms are sitting on there. I know how big the balloon would be if I were occupying a volume of a gaseous product. So that's the purpose of the mole, is to measure matter and be able to exchange its units. Just as we have certain words that represent numbers. If I say the word pair, I have a pair of mittens, I have a pair of socks. You know that that word pair represents the number 2. If I have a dozen eggs, that word dozen represents a number, and that number is 12. A ream of paper, unless you stuff the copy machine regularly like I do, a ream of paper is 500 sheets. It's a word that represents a number. These words and the number is the same thing as a chemical mole. The mole represents a number, and it's a very, very, very big number because atoms are so small. When I think of the word mole, it's a number, and it's called Avogadro's number, and that is definitely a real picture of Amadeus Avogadro. I know. It's a little scary. I'm just watching your faces go, ooh, I hope his mother loved him. He kind of, hey ladies, 6.02 times 10 to the 23rd is called Avogadro's number. He did not count it. He did not determine it. It was an honorary naming of this scientist. Avogadro's number is 6.023 times 10 to the 23rd power. That's 23 zeros after that number. Do you see how significantly large that number is? If you were to take a grain of sand, how tiny is a grain of sand, and have a mole's worth of a grain of sand, not just one, but a whole mole, 6.02 times 10 to the 23rd grains of sand, what would it occupy for space? Would it fill a bucket? Would it fill this room? Would it fill the city of Long Beach? Would it fill the state of Mississippi, let's say like 1 meter high? How much is it? Take a guess. How big is a mole? Would it fill, I can't fill the world because that would be too much. What do you think? How big is big? The little story that you'll read about is in your text. If you had 1 mole of sand, it would cover the entire state of California, which is not a tiny state, it's a rather large state, 10 meters deep. That's a mole of sand. That's a big number, isn't it? So how small is an atom compared to a grain of sand? Dinky dinky, isn't it? Because what does a mole of atoms look like? If you had a mole of atoms, let's say you had a mole of zinc, because didn't you use zinc last week in your lab for the displacement? If you had a whole mole of zinc, how much would that look like? Would it fill the room? Would it fill the building? Or would it fill a little weighing tray? A little weighing tray, that's right. I'll tell you, a whole mole of zinc would occupy exactly 65.38 grams on the scale. That's a mole of zinc. If I wanted a mole of carbon on the scale, I would weigh out 12.011 grams of carbon. That would be a whole mole of carbon. Not very much, but it would fill a little weighing tray. If it were a grain of sand, it occupies an entire state. It's a massively large number because atoms are so darn tiny. Why is it that number, 6.02 times 10 to the 23rd? What's so special about that number? That happens to be the number of atoms it takes to sit on the scale for any atom to give you the atomic mass on the periodic table. If I wanted to weigh out 1 whole mole of the sulfur atom, it isn't just counting 1, 2 atoms, 3 atoms. You could not do that. But you can weigh out 32.06 grams of sulfur and now know with confidence there's exactly 1 mole of sulfur, 6.02 times 10 to the 23rd atoms of sulfur. I can count by weighing, and how much I weigh is found on the periodic table. That number, Avogadro's number, tells me how many atoms it takes to achieve the molecular weight on the table. So it's a derived number. It's not been counted. It's been derived based on the weights of the atoms. I'm going to introduce some vocabulary: gram atomic mass, gram molecular mass, gram formula mass. It just depends upon what it is that you're weighing. If I go to the scale and I weigh out atoms, atoms are the building block of elements. If I went and weighed out carbon, think of like a lump of coal as carbon, the black soot carbon. I would be weighing atoms of carbon. That's its building block. The gram atomic mass is 12.011 grams, the mass of 1 mole. If I'm weighing atoms, gram atomic mass. Sometimes I'm weighing compounds, not just elements, but compounds. And we know compounds come in 2 different flavors. They can be molecular or they can be ionic. We know that molecular compounds are built of molecules. If I wanted to know how much would I weigh out to get a whole mole of water molecules, see how 2 H's and an O bond together? All of them are non-metal, so it's a molecular compound. Water exists in nature as a molecule, so it has a gram molecular compound. How much would you weigh out? Well, the secret still lies on the periodic table. I have 2 H's and an O. How much would you need to weigh out? Well, each hydrogen would contribute 1.008 grams. There's 2 of them. And an oxygen essentially is 15.999. I'd call it 16. I'd weigh out 18 grams of water to get 1 mole of water molecules. Gram molecular mass, molecules. Sometimes we have to weigh out salts, ionic compounds. Their building blocks are known as formula units. We commonly call them salts. Metal to the nonmetal, crisscross charges, you're making ionic compounds. If you go to the scale and weigh out salt, let's call it sodium chloride is one example. How much would you weigh out to get a whole mole of sodium chloride formula units? Again, the secret's on the periodic table. Sodium, with its mass of 22.989, call it 23. Chlorine with a mass of 35.45. Add those together to find the mass of a whole mole of sodium chloride. With sodium's mass and chlorine's mass, I add those together, and now I know how much to weigh out to get 1 whole mole of sodium chloride. Why are there 3 different words, 3 different vocabulary words? Just simply because we weigh different things in chemistry. We can weigh atoms, molecules, or formula units. It's a very specific term based on what it is you're reacting, you're weighing out. I tend to use this word called molar mass. It's like the big umbrella to mean anything. If I don't want to be specific to let you know if it's an atom, a molecule, or formula unit, I can just call it the molar mass, and now I've accomplished all 3 of them. So one word to define anything you weigh out, 1 whole mole of anything, would be called its molar mass, the mole of any substance. That's the term that lies on the mole map, is the term molar mass. How much do you weigh out to get a whole mole of substances? Let me pause and ask for some conversation with a neighbor related to this picture. What do you see in the picture? What do they represent? What is that picture? Please talk. These are little pieces of filter paper, right? So they're about this big piece of filter paper, and you see a mass written under each one. Where do those masses come from? Beautiful. The periodic table. The element named zinc. The element zinc has the symbol Zn. It's the element you used last week in the lab when you determined its density. It has an atomic mass of 65.38. 65.38 grams of zinc on that piece of filter paper. That's the amount of 65 grams of zinc. That's 1 mole of zinc. That is exactly 6.02 times 10 to the 23rd atoms of zinc. I didn't count it. I weighed it. But I know how many atoms there are because I can relate that to the mole. There's your 12 grams of carbon, 24.3 grams of magnesium, 63.5 grams of copper. That's copper wire. You see tin, lead, silicon, and sulfur. Why don't they all have the same mass if they're all the same number of particles? Each one of those pieces of paper has the exact same number of particles on it. Why don't they weigh the same? Tell your neighbor. Are all atoms the same size? Not at all. It's like asking, would a mole of ping pong balls weigh the same as a mole of bowling balls? I have the same number of them, but would they weigh the same? Obviously not. They have different masses. Atoms come in different sizes, just as the bowling ball and the ping pong ball have different sizes. So the secret of finding those lies on the periodic table. On a piece of paper to turn in today. Tell me the gram atomic mass of carbon, of hydrogen, and of sulfur. When I define the term gram atomic mass, I'm telling you that I want to know how many grams to get exactly 6.023 times 10 to the 23rd atoms of each of those elements. Tell me the gram atomic mass. Friends, sometimes I abbreviate that, gram atomic mass. How much would you weigh out to get a whole mole of each of those elements? Let's agree to carry 1 decimal from the periodic table. So if we're wondering how many decimals does she want me to grab, and each periodic table is just a little bit different. Some have many decimals, some have 1 or 2. Let's agree to carry 1 decimal when reporting any molar mass. So for instance, when you found carbon on the periodic table, in the box it said 12.011. If we carry just 1 decimal, I would weigh out 12.0 grams of the element carbon to have exactly 1 mole of carbon, which is the same as saying 6.02 times 10 to the 23rd atoms of carbon. So for carbon, when I found it on the periodic table, 12.011 was the number I found for the mass number, and that's what I'm carrying 1 decimal. When I found the element hydrogen on the periodic table, it's the very first one. It says 1.008. Yours might be different if it just rounds a little different or has a different number of decimals, but I'm going to call that 1.0 grams of hydrogen. Atoms of hydrogen would weigh 1 gram. And sulfur, when you see that on the periodic table, sulfur has an element S. It says 32.06. Rounding correctly, we should carry that as 32.1 grams. So that's what I'm asking is let's carry one decimal so we have a common theme as we proceed in our work. So we've just written what's called a gram atomic mass for each of these elements. Keep that work going on your paper. Do the following for the molecules of sulfur trioxide, a molecule of hydrogen, and a molecule of carbon dioxide. I remember learning for nomenclature, nonmetals hooked to nonmetals, we use prefixes in their names. Mono, di, tri, tetra, counting with the subscripts. So when I hear subscripts, I hear those prefixes, I know it's molecular compounds. The gram molecular mass, GMM for abbreviation. If I can't write a formula, I can't get the molar mass, and I therefore won't be able to calculate a mole. That's a fundamental skill that carries from the entire course, being able to write a correct formula so that your math comes out correct. It has to just flow from you with a lot of tool pages till you get good at it. No, I'm asking for grams, not how many atoms. There's going to be that many molecules at the end, Avogadro's number, but I just want a gram unit. So gram molecular mass, how much would I weigh out to get a mole? Absolutely, just what we did. Perfect. So for instance, sulfur is the element S, trioxide. How does that feel? Hearing the word sulfur trioxide, are you able to go, oh, that's SO3? If not, please keep practicing. It's a fundamental skill, and it just takes repetition, as any new language does, right? You need to speak it to get better at it. We looked up sulfur a moment ago, and it had a molar mass of 32.1. There's one sulfur in that compound. It's contributing 32.1 grams to the entire compound. Oxygen, when I looked it up, said 15.999. If we carry one decimal, it will round to 16.0. So with oxygen, there's 16, but there's 3 of them there. Each of the oxygen weighing 16. So the total contribution from the oxygens is 48 grams. When you add 32.1 and 48, you get what's called, I didn't hit that right, 32.1 plus, I multiplied, you get 80.1 grams of sulfur trioxide. Just adding the individual atoms together gives me the molar mass, the gram molecular mass of that compound. On the previous screen, I asked you for the gram atomic mass of hydrogen. Here I'm asking you for the gram molecular mass. That means hydrogen is now a molecule. There are 7 molecules, that elements of the periodic table that exist as diatomic molecules. And I've asked you to memorize those or somehow print them on your periodic table somehow. We even had a funny sentence, horses need oats for clear brown eyes. There are other mnemonic devices to help you as well. A molecule of hydrogen is H2, therefore its gram molecular mass is 2 grams, 2 H's added together. Carbon dioxide has a molecular formula of CO2. Carbon, who has an atomic mass of 12.0, oxygen has a molecular mass of 16, but there's 2 of them there. So I take a carbon, add it to 2 oxygens, and get the sum of all 3 atoms together. A C added to 2 O's, 32 and 12, that should be 44 grams of carbon dioxide. It's a molecular mass, not an atomic mass. Here's an atom of H. Here's a molecule of hydrogen, two atoms bonded together. It's a great reminder, an atom versus a molecule. Two H's bonded together to create a single molecule weighs 2 grams. An atom of hydrogen, you would not trip over an atom in nature. It's too unstable. It's got to be hooked to something else. The last part, and I'm just really being sneaky, and it's my way of making you practice nomenclature, really is the drill here. Keep going on your paper to turn in. I want to see the nomenclature. Tell me the mass of sodium chloride, ammonium carbonate, and potassium oxide. I have to see that you can write formulas to build a foundation to do a mole calculation. Since I know these are formula masses, I know these are ionic compounds, I have to consider charges when I write out their formula. So your tool pages, the periodic table and the polyatomic ion chart, those are your two crutches here to be able to write correct formulas. Write the formulas on your paper to turn in, and then sum each atom to tell me the formula mass. Remember for your test day to have a physical copy of your periodic table. It cannot be from your lab book, all right? Make sure you print one. That you have a polyatomic ion chart printed, and that you have the mole map printed. They can't be electronic, they can't be from a book, but they can certainly be out as long as they're individual pages. I think what I'm noticing is if you're feeling stuck, it isn't the new part about math, right? It's the formula writing that we still need practice with. And I'm just encouraging you that it's a normal feeling, that proficiency with that, it just takes time and it takes practice. Keep practicing the nomenclature, writing formulas, naming formulas. That has to be ingrained and go quickly. If you've not yet taken your periodic table and placed your charges in each and every box, I highly encourage you to back up and find that lesson with me and get those in there. It makes formula writing very simplistic if the charges are staring at you. For instance, when I find sodium in the box of sodium with me in a lesson, I wrote the charge. Any element in this first column, we wrote the charge as +1. When I found chloride, Cl, I wrote in the box that its charge is -1, that any element in that column will always be a -1 charge. And when a +1 sodium bonds to a -1 chloride, you have a formula that comes out electrically neutral. +1 and a -1 is 0 overall, so no subscripts are needed. It's just simply NaCl based on charge. If sodium has a molar mass of 23.0, chlorine has a molar mass of 35.45, so I'll round that to 35.5. I add the two atoms together to get a gram formula mass, and that would come out to 58.5 grams of sodium chloride. Notice how I'm including the label gram of sodium chloride. Please get in that habit to make sure we keep track of what we're weighing. Ammonium carbonate. I'm going to bring that down so I can write bigger. Ammonium is our positive polyatomic ion. It's found on the polyatomic ion chart way to the right-hand side, kind of down low. You see it? There's just one positive polyatomic ion called ammonium. Its last name was given as carbonate, the ATE ending. We're stressing when you hear ate or ite that tells you it's a polyatomic ion. I have to find carbonate. On your polyatomic chart, it's the center column, maybe quarter of the way down, see carbonate. Polyatomic side, not periodic table side. 8 tells me polyatomic. It has a formula of CO3, and it carries a -2 charge, carbonate. Does a +1 balance the -2 to be electrically neutral? No. That tells us we need to crisscross our charges. When I crisscross charges, I bring them around and down, not the sign, positive or negative, but the number, because the subscript is a quantity, it's not a charge. When I need to take more than one polyatomic ion, I put it inside a parenthesis, so I can take a group of them. NH4 taken twice, CO3. That's the chemical formula for the compound called ammonium carbonate. I'm trying to integrate that last week's lesson to help us kind of keep practicing. Ammonium carbonate built of 2 polyatomic ions. I crisscross charges. In order to take groups of polyatomics, we have to put it inside a parenthesis and the subscript outside. So now, with the next new part of our lesson, we're trying to calculate how much would I weigh out to get 1 whole mole of that compound. Inside the parenthesis, that N is taken twice. So if nitrogen has an atomic mass of 14, there's 2 of them there. The total weight comes out to be 28 grams just from the nitrogen element. Inside the parenthesis is a hydrogen. It has a gram atomic mass of 1.0. I'm just pulling these from the chart. When you look them up so often, you'll just start remembering them. You'll start to just know carbon is 12, hydrogen is 1, and it saves you a little bit of time once the repetition occurs. How many hydrogens are in that compound? There's 4 taken twice. 4 times 2 is exactly 8. Excellent work. So its contribution would be 8 more grams to the compound's molar mass. Carbon has a formula weight of 12, oxygen is 16, and there's 3 of those. I want to sum each atom to find the total mass that we'll call the gram formula mass, or a general vocab called molar mass. So on my calculator, I'll add 28 plus 8 plus 12 plus 48, and I find a total of 96 grams of ammonium carbonate. We are building, kind of looking at the mole map where this is heading. This becomes the exchange unit to bring us from the scale where we weigh things into the central unit called the mole. How much do I weigh out is known as its molar mass. And the third one I asked you to do is potassium oxide. This is a binary compound built of 2 ions, potassium. Potassium is found in the first family on your periodic table. In the box of potassium, I asked you to write its charge. Any element in that first column is always a +1 charge. Oxide comes from the element oxygen. I'm hearing "ide" because it's an ion. The negative ion ends in "ide." Oxygen, inside the box, I asked you to write its charge. Any nonmetal in group 6A will carry the -2 charge. We wrote that. It has to gain 2 to have 8. So if K is a +1, O is a -2, and I just like to write the charges up high. It's not part of the formula, but it's just a tool that helps me figure out the formula so that when I crisscross, I can bring those around and down and know the subscripts for that compound. Potassium oxide has a formula of K2O. 2 potassiums and 1 oxygen. Potassium has a formula weight of 39.0983. If we agree to carry 1 decimal, I'll call that 39.1. But there's 2 of them there. Oxygen weighs 16, so I'm going to sum 2 Ks and 1O. And did you find 94.2? Excellent. So we went through atoms, molecules, and then formula units. So far you should have, is it 9 little mass numbers on your paper so far? So that term, molar mass, that's the exchange unit that we'll use that brings us from the weighing into the center of our mole map known as the chemical mole. The exchange unit called molar mass, the mass of any compound, the mass of anything that I want 1 mole of, is referred to as the molar mass. And I just reminded myself to remind you to be careful about the 7 naturally occurring elements. It may be vague. If you hear what's the molar mass of hydrogen or chlorine, bromine, iodine, any of those 7 elements, this is a vague term. I would need to know specifically, do you mean an atom or do you need a molecule? So with those 7 elements, we just want to be careful to be very precise in the language. Otherwise, the general term molar mass works fine. What's the molar mass of? And then you just add the weights off the periodic table. Without calculating, not a numerical answer, this is a conversation. Could you check in with a neighbor to make sure you have the same understanding of the process? Describe with your neighbor, how would you find the molar mass of ibuprofen? Ibuprofen has the chemical formula I wrote bigger up on the screen so you can see it. Without solving, discuss the process of what you would do. Please talk. I cut you off. I hooked ammonium to carbonate.
Now, where do we get
This side. I can't even read that. Maybe you can. Well, give yourself some time, bring it back. We're just looking up these weights and adding them together. It's just addition. You're trying to do next steps, I think, yet we're not yet there because you have a bigger picture of what we've been doing. Yeah, we're not there yet. We haven't moved yet. We've just tried to figure out conversion factors. Yeah, perfect. I like the lecture pause just to check in and make sure what I'm saying is clicking. And what really cements the learning is making you say it in a different way. Saying it to a neighbor actually solidifies your own learning. So thank you for engaging. And what you're discussing is the process, really, and just kind of sharing how you found the weight of each of the elements from the periodic table. These numbers are what we found off the box of each element. And then you took the subscript to determine how many there were. You're multiplying each individual element's contribution to the total to sum to find the entire mass. So the process is what we did, no need to solve there. What I'm gathering is that it's the formula writing that might stumble, but I get the idea of adding so far. So we'll continue practicing as best I can, sprinkling in nomenclature practice. How about, I'm going to cover that up for a moment. If someone asked you to find the molar mass of aluminum sulfate, work with your neighbor to discuss what the formula is for aluminum sulfate. Can we get that far through a discussion? Aluminum sulfate. Time to go.
Now jigsaw is completely different.
Okay. Excellent. So I like what you're doing because you're helping yourself count how many there are. Comfortable? Good. So my front vantage point, it's all about the conversation and reminding each other, okay, how do I know the charges? Where do I find this? Where do I find that? And that truly deepens your learning. So compliments to the engagement and conversation, as simplistic as that question might be, there is a lot of talk going on, and that talk is very helpful in remembering nomenclature. So when I wrote aluminum sulfate, you said, okay, aluminum is this element, it has a symbol Al. I found that from the periodic table. And in the box of aluminum, I wrote myself its charge. You're doing yourself a favor if you go back and make sure your charges are written in the periodic table, on the periodic table that you'll be using on the test, right? Not some random other one, but the test-taking tool page. I can see aluminum is a metal in group 3A. It will lose 3 electrons. It's a +3 charge. From the polyatomic page, and I know it's polyatomic because I'm hearing 8, right? 8 and ite, those endings tell me that it's some kind of oxygen, polyatomic. Sulfate is SO4, and it carries a -2 charge. A +3 and a -2 do not balance, electrically balance to 0, so I know I need to crisscross. The crisscross tells me to come around and down to place as a subscript. Subscripts don't have charges on them. It's a quantity, so don't grab the negative with it. Just bring the 2 around and down. And that this 3 tells me I'm going to need 3 groups of the sulfate ion. So if I group polyatomics, I have to place them in a parenthesis. And I read that as saying Al2, SO4 taken 3 times. That's how we read that formula. Aluminum, there are 2 of them in that formula. And when I find the molar mass of aluminum, I would call it 27, 27.0, carrying the 1 decimal. When I find sulfur on the periodic table, it rounds to be 32.1. How many sulfurs are in the compound? Beautiful. Don't forget to distribute through the parentheses. There's 3 of them. And then, of course, oxygen. Distribute, don't add, but distribute means to multiply. There are 12 oxygens in that formula. And I would add together 2 aluminums, 3 sulfurs, and 12 oxygens to find the molar mass of aluminum sulfate. And you did that through that process. We found 2 aluminums, 3 sulfurs, 12 oxygens, and we found their sum. I didn't bother, but you would add to find about 342. I really think the addition part is fine. We're just still practicing nomenclature, and we'll continue to do so best we can. Now, let's begin using the molar mass, this very skill, and start applying it to traveling on the road map. The mole map allows us to exchange between units. Let's put this one on the attendance sheet. There's 2 of them here. Let's agree to just show the first and let you keep the second for your set of notes. On the attendance paper, turn number 1 in, and then you can keep your notes for number 2. The first one says, find the mass in grams of 3.32 moles of potassium oxide. The unit that we are given is the mole unit of potassium. The given quantity is 3.32 moles of potassium. That places me here in the center of the mole map. The unit mole is the center, and then I just covered the word, the mole. What we want to know is the grams of potassium. The grams are measured on a scale, so we're heading from the center of the mole out to the scale. And using the mole map, it creates this visual that literally you trip over the conversion factor to bring you from one unit to the next. If I'm standing in the center and want to head out to the scale to measure something in grams, it literally gives me the conversion. It says molar mass per 1 mole. What is the molar mass in a mole? My work would look like this. I'm going to start by writing 3.32 moles of potassium. I want to then set up a conversion factor, and some of us like this railroad track. I want to set up this conversion factor that cancels the moles and brings me to the gram. The molar mass in a mole, molar mass per mole. So how many grams does a whole mole of potassium weigh? I want to say 39.1, carrying that 1 decimal. My mole unit's canceled, and I'm left with the unit called grams. I'm going to just simply multiply moles times molar mass to come out to a gram. Whenever I'm heading out of the mole map, I multiply. I don't care if I go north to the volume, down here to counting, or down to the scale. When you head out from the center, you multiply. And we'll soon see one where we go in means to divide. What's 3.32 times 39.1? Carrying that 1 decimal, and we'll get 129.8 grams of potassium. We use the molar mass to exchange from the unit mole out to the gram unit. We traveled from the center out to the scale. In our second problem, we're still being asked to solve for grams, so I still want to know a mass, and the unit that I'm given is the mole. 4.52 times 10 to the negative 3 moles of glucose. I can set up a conversion factor that will cancel the word mole and bring me to the gram. What is the mass of 1 mole of glucose? That was the fundamental skill we were just practicing. So to travel the mole map, I have to know to add 6 carbons, 12 H's, and 6 O's. I don't need to show that work on a piece of paper. I just do that on my calculator. If I take carbon, and there's 6 of them there, I'll add that to hydrogen, and there's 12 of them there, and on the oxygen, there's 6 of them there. Add together 6 carbons, 12 H's, and 6 O's. That sum of those atoms is what we refer to as molar mass. And the molar mass is what exchanges for me between the mole and the scale. When you add that, I want to say it's 180 is its molar mass. Taking 180 grams of glucose times the number of moles, 4.52 times 10 to the negative 3rd. Anyone else get 0.815? Let's see, 3 Sig Figs. That's not a mole. Oh, I have a screen error. I did 4.53 instead of 4.52, so I'm probably off a little bit, aren't I? How about that? We'll let that go. I hit it wrong, but I'll trust you that you didn't. I did. I accidentally put a 3 here instead of a 2, so my answer was off a little bit. It is what your screen says, I bet. 0.814. I'm taking that And no one's yelling, so it must be agreeable. Thank you. I swear, when you try to talk, write, and calculate, something falls apart. Let's try an opposite direction. This time, you can keep these. I just wanted the one. You can put your attendance paper. You want these examples. I would like to calculate moles from nitrogen gas. So let's talk strategy as I look at this question. Number 3 is what we'll focus on. Let's calculate the number of moles. So what I want to find is a unit called mole. And this time I'm given grams of nitrogen gas. When I think about where I'm at on the mole map, where I'm starting and where I'd like to travel to, that's the purpose of a visual like this. How many conversions gets me from place to place? Where I'm starting at this time is at the scale. This is the beginning of my journey, the gram unit. And I want to go into the mole unit. So my journey has me starting at the scale with a one-step conversion into the mole. Convert grams to moles, follow the arrow in, and you'll literally trip over the conversion factor on this visual. This time the conversion says put the mole unit on top and the molar mass unit on the bottom, which means to divide to head in. When you set up the work for number 3, we have 75 grams of nitrogen gas. When I read nitrogen gas, I have to remember that horses need oats for clear brown eyes. What is the formula for the elemental form of nitrogen? It's N2, diatomic. That I would be incorrect if I wrote just N and used 14 for the molar mass. I have to use 28 for the molar mass. Now notice here I want grams to cancel and I want to end with the mole. The mass of 1 mole of 2 N's added together is 28 grams. 2 N's added together. So I divide to head into the mole. 75 over 28, and I get 2.68. I should have 2 Sig Figs. 2.7 moles of nitrogen gas. My 4th example, I tried to integrate a little metric system, kind of a little bit of review there. It says, let's calculate the moles given 0.25 kilograms of sodium oxide. So some skills that this question requires, I have to first of all remember how to change a kilogram to a gram, because molar mass is in a gram unit, and I have to have like units. So I've got to do a little switch of the decimal there. Kilo has to become gram. And I have some nomenclature skill there. I have to read the word sodium oxide and be able to write a formula to know what to add to find a formula weight. So we want to know how many moles given a gram. I'm starting at the mass, the scale, and I want to head in. The first skill, 0.25 kilograms converted to a gram. The kilo is the prefix that represents 1,000, right? So it takes 1,000 grams to equal a kilogram. Do you have that little chart made for test taking tool day? The little metric staircase is what I recommended. That way, if you want to memorize all the prefixes, more power to you, but I did say that that would be an allowable test-taking tool page. If you want to have help remembering those. And some of you are using a mnemonic device that works something like King Philip came over, or so, I don't remember that. King Henry, wrong guy. All right, so whatever works for you, but have that crutch there. So that when you transfer this, you're sliding the decimal 3 spots left. So 250 grams when you multiply that out. Is that right? What's 0.25 times 1,000? Perfect. So that's my starting, 250 grams of sodium oxide. Sodium is a +1, oxide is a -2, so my formula is Na2O, sodium oxide. I have to remember to check charges, crisscross, and write a correct formula for sodium oxide. My conversion factor will cancel the gram and bring me to the mole. I divide by molar mass at this point. Sodium has a molar mass of 23, but there's 2 of them there. Oxygen has a molar mass of 16. 46 and 16 is 52 grams. Just testing you. Not really. Carrier 1, most days of the week, would give that a 62. That's me in mental math. Not so much. But I can do it with the calculator. 250 divided by 62, and do you find 4.03 something? And that unit ends up to be moles. Take a break with your pencil and calculator, converse with your neighbor, make them explain, how do I know whether to go into the mole or out of the mole? How do I know which direction I'm supposed to be traveling? Talk about that for a moment with a neighbor nearby.
If you're trying to get
I think it even yells at you, please print. All right, well, let's try traveling a new road, shall we? We're all warmed up on this scale to the mole. This allows us to turn grams into mole. I'd like to next explore a second way we measure matter, and that's by counting the number of individual particles. Do you see this visual is supposed to be looking like individual atoms all kind of stacked together? So individual atoms called representative particles. Those particles is kind of a general term. In chemistry, those particles will either be atoms, molecules, or formula units. And yes, I abbreviate formula unit as the ever popular FU. And in chemistry, that's a nice thing to say. Oh, a formula unit? Okay, FU too, right? That's just what it is. Atoms, molecules, and formula units. That means individual elements, molecular compounds, or ionic compounds. Sometimes we call those salts. That's what those little jelly beans, little Skittles or something, that's what they look like. Those are the individual pieces. So now the word clue says how many atoms are in this many moles of carbon. So visually, I'm given the unit mole, but I now want to travel a different direction. I want to go down and count the individual atoms in that mole. That means I'm heading this direction on the mole map, from the center down to the individual pieces. And when I'm at the center and I head out, I literally trip over my conversion. I've learned that there's an Avogadro's number of atoms in a mole. Avogadro's number is 6.023 times 10 to the 23rd. I often just write 6.02 and get close enough to the answer. I most often don't carry the 6.023, simply because the number in the problem rarely gives me that many decimals. So the work would look like 6.79 moles of carbon. I'm going to set up a conversion factor where the mole unit cancels, and I'm at the individual atoms of carbon. By definition, you can see on your visual that 1 mole is equivalent to saying 6.02 times 10 to the 23rd atoms of carbon. Please do not wait until test day to figure out how to enter scientific notation into your calculator. Most often, if you wait for test day, you'll be off. And every calculator is just a little bit different. Some have times 10 to the buttons, like a race like here. Some have an EE key, that's what mine has. Some have an EXP key, depending upon the brand name. Can you take a moment with your calculator and just put your finger on the button that you believe to be scientific notation? Got it? Just making you take a moment and find it. If you have a Texas Instrument, you most likely have an EE key. If you have a Casio, you most likely have a times 10 raised to something. Or sometimes I see it as EXP on a Casio. I'm not too familiar with Casios. I've just always owned Texas Instrument, not because there's a special or anything, it's just what I've had. If you don't find it, ask your neighbor to look on your calculator and see if they can help you. So, yes, it will be. Let's solve it and see if we can't, let's make sure we get a common answer. My key sequence, mine on my calculator, I have a Texas Instrument, my key sequence would look like this. It would be 6.79 times 6.02, and then I have to press second function. That's the blue button on mine. And then I hit on top of the comma, I have an EE key. That's on top of the comma. And then I'd hit 23 equal. That's my key sequence. It may or may not match yours if you have a different brand. So let's hit that and see if we get a common answer. 6.79 times 6.02, second function EE, 23. My screen reads 6.1, and I'll just round 2, times 10 to the 24th atoms of carbon. Oh, I hit a 9 and not a 6. Dang it. Just checking. I know you're really hitting because you're finding my calculator boo-boos. What if I said it really was equal to 4.1 times 10 to the 24th? Now I have more confidence because people said that's what I got instead of what did she do? That makes me feel better. Oh, you're checking Sig Figs? So that particular question, let me scroll up and look at Sig Figs. So we had 3 Sig Figs given, so my answer should include 3, so 4.09 would be a better answer. I was happy I got to the about right answer. Maybe you get like that too, right? I'm just practicing this to make sure that, come test day, you have a common answer with me so that the pressing of the sequences might be different depending on your own calculator. Just make sure that you're coming up with the same answer. Okay, excellent. Anybody in that boat? Casios? They are foreign to me just because I've never owned one, so I appreciate having a go-to gal. Alrighty. So let's try one more, and I'm going to say on one to turn in today. Let's try this, and then we'll try a two-stepper. Let's try number 7. On the turn-in paper, please. How many formula units are present in 9.39 moles of sodium chloride? In 9.39 moles of sodium chloride. So remember, the building block of an ionic compound is called a formula unit. A building block of elements are called atoms. A building block of molecules, a building block of salts. So don't let the vocabulary word kind of throw you. I'm calculating formula units. It's just a vocabulary match. A formula unit of an ionic compound, that's what they're called, just as elements would have atoms or molecules. We want to make sure it's a vocab match. So it's still just a one-step process. Even though the vocabulary has changed, it's just because I'm counting a salt instead of an individual atom. I still know that 1 mole of anything would contain an Avogadro's number of particles. This time the particle is called a formula unit. The formula unit is the basic building block of any salt. So we call it, I write it as FU. I know, but it saves hours. Given a mole, we want to know the number of particles. We know to multiply to head out. We're going to multiply our mole number of 9.39 times Avogadro. I wrote mine, and I wouldn't mind if somebody just nodded, say, yeah, I got that, before I quickly erase and re-hit, right? So we've traveled from moles to the scale. We've traveled from moles to the particle. We're just using different exchange units because we're heading in different places. There is a north on our mole map. It's to the world of volume, where we learn that 1 mole of any gas is 22.4 liters big. That's kind of pulled out later in the lesson, so I didn't really spend time with those examples now. The 2 main roads presented in our chapter, from the scale to the mole, and from the mole to the individual particles. It's not until we get to the gas laws later in our journey that we'll head north to the land of the balloons. So out of the 3 roads, focus on those 2 as you perfect mastery. I'd like to model some from your homework, so you might want to keep these. You'll see these on sapling. I said let's be cautious of what we call a vocabulary mismatch. What I'm referring to is, I'm kind of just reading it through, number 8 is a vocabulary mismatch. How many sulfur atoms are present in 5 moles of aluminum sulfate? I'm asked to count individual atoms of sulfur, but I'm given something much larger called a compound. When I see that, I know that it's kind of a trigger for me, a word clue, that it's going to be a 2-step conversion factor, a vocabulary mismatch. So I'm going to begin by writing down the unit, which is 5 moles, and then it gives me the name aluminum sulfate. We've written that a few times. I have aluminum, which I know carries a +3. Sulfate is a polyatomic, carries a -2. So when I write aluminum sulfate, we get Al2, parenthesis, SO4, taken 3 times. That's my formula of aluminum sulfate. My first conversion factor needs to cancel the mole and bring me to the individual particles of this compound. Is this compound an element? Makes no sense. Is it a molecule or is it a formula unit? What type of particle is this salt? Perfect. It's a formula unit. Even if you wrote the word particle, and that's fine, you realize that it's a compound and not the individual sulfur atoms. I know that there's 6.02 times 10 to the 23rd formula units of my compound, aluminum sulfate, in every 1 mole. That's your first conversion factor. I have the moles canceled, and I'm at the compound aluminum sulfate. But what does the question ask me? It asks me to go a little bit deeper, doesn't it? I'm not asking about compounds, I'm asking about individual sulfur atoms. in every 1 formula unit, how many atoms of sulfur do you see? I see 3 as well. The parenthesis taken 3 times, that 3 is talking to the sulfur. There's 3 sulfur atoms in every one of those compound formulas. So what I'm referring to as a vocab mismatch, I just mean that if I'm asked to count something smaller than the substance they gave me, you should be suspicious that it's a 2-step conversion. I've got to count something inside smaller than the compound they gave me. So I'm going to take 5 times Avogadro's number times 3, and I got an error. How about something like 9.03 times 10 to the 24th? Yay for me. Pause with your neighbor and just make them describe to you, just check in with one another. How did we know there were 2 conversions in that one instead of 1 that we've been practicing so far? Number 9 allows us to practice kind of that same skill, and you'll see this one on your sapling. So let's set this one up as well. Same skill. How many moles of N are in 0.175 grams of N2O? There is a clue there that lets me know that there's 2 conversions involved. What does that clue look like? What's the trigger to let me know 2 conversions? Beautiful, absolutely. What she said was it's asking about a particular atom inside something bigger, right? The bigger molecule has some N's in it, and we're going to focus on that. I call it a vocab mismatch. That's my clue that we're going to have 2 conversions. So I'll start with my 0.175 grams of the molecule N2O. I want to go into the word mole, so I know to place moles over grams to cancel the gram. Now, visually on your mole map, you're down at the scale and you want to head in. That's the direction we're heading. And when you head in from the scale into the mole, you literally trip over your conversion. It says place 1 mole over the molar mass of your compound. That's our first conversion. I've got to add 2 N's at 14 apiece to 16 from the oxygen, and I get a molar mass of 44. Right now, I'm at moles of the compound N2O. Let's look deeper. In every mole of your compound, how many N's do you see? 2 of them. Whoops, that's supposed to be nitrogen. I'll divide to head in to make that a mole unit, and then notice that there's twice as many atoms of nitrogen per mole of compound. So when I solve for this, 0.175, I'll divide by the molar mass of 44, and then multiply by 2 the number of nitrogen atoms. And when I solved, kind of tiny, 0.00795, but I'll look up. I got 2 people to nod so far. Anyone else? Same answer? If I stare at you long enough, that's what I'm doing. Please confirm my math. As I'm presenting, I really love Calculator Buddy, so feel free to yell if I make a mistake. It happens because I'm trying to do too many things at once. And if I'm chewing gum, things really fall apart. My answer to that is if it's necessary for significant digits, then sure, it must be. But other than that, I don't care because I read them one or the other. So for instance, her question was, do I have to place scientific notation? And my answer is no. I read them as the same thing, unless you need it for Sig Fig reasons. Here's some more sapling, and I wouldn't mind just taking as many few minutes that are left to continue practicing on the homework questions to give you a flavor of how this will come out. This is another screenshot, and I just put it below that on the sapling if you have your printed slides. We need to start with a formula, and then once we know the formula, we're going to apply a math question to it. So again, even though you've kind of wrapped up your nomenclature lessons from Chapter 2, I really tried to keep integrating the practices into the current chapter just because the repetition is our friend as we're learning. I see copper Roman numeral 2 phosphate. That Roman numeral 2 is mandatory in its name because copper lives in the heart of, I don't know your charge by where you live. It's in the shorties, the group B transitions. Because it has a variable charge, I tell you the charge by using the Roman numeral. So that Roman numeral tells me the charge, not how many there are. That's a common mistake. Sometimes I'm confused that the Roman numeral 2 tells me to put a subscript 2 there. That's not what it means. Copper is carrying a +2. That's the meaning of the Roman numeral. The polyatomic ion called phosphate. Notice the ATE. That tells me to check out my polyatomic chart and just stare it down until you find it. You'll become more and more familiar with those the longer you stare at the chart. Phosphate is a polyatomic ion. It's PO4 and it carries a -3. When you crisscross, we read that as Cu3, PO4 taken twice. That's how you read that formula, in the parenthesis, taken twice. So that's the first skill. Once we get the formula down, we're then practicing the mole map skill. How many atoms of phosphorus are in 3.5 moles of copper 2 phosphate? How many atoms of phosphorus? How many conversion factors would you predict just based on the word clues in that story problem? I agree. Beautiful. You know it's 2 because we're counting something smaller than the compound we just wrote. We're going to count individual phosphoruses. That's weird. We're going to count the P's inside that formula. So we're going to start by writing its number, 3.50. Its unit is a mole unit, and its formula, copper 3 phosphate. I'll set up a series of conversions that cancels the mole and brings me to the number of individual particles. And that's an Avogadro's number, right? Counting is Avogadro. And what I'm counting is this ionic compound. Anytime you crisscross charges, they're built of ions, and their building blocks are called formula units. The compound is called a formula unit. We know that there's an Avogadro's number of copper 2 phosphate formula units per mole. But I'm not yet done because we wanted to know individual atoms of P, phosphorus. Look inside the formula and how many P's do we count? Thank you, because those who answered based on what I wrote were correct. Those who answered based on what I should have wrote were also correct. It's 2. Cu3, PO4 taken twice. I accidentally carried a 3. There are 2 phosphorus atoms per formula unit. So again, just to practice with what I call a vocab mismatch to let you kind of trigger, oh, this will need a next step before I'm done. 3.5 times Avogadro times 2 solves for the problem. Can you put that down? I'll do the same and see if we get a common answer. How about a thumbs up if it matches, just to give me an idea? Yay. Okay, that's good. I think I'm proud of myself. I hit that one right. Okay. So today we practiced mole map skills. We integrated nomenclature. I'm going to continue to do so best I can. When we come back Thursday, we're going to talk about empirical and molecular formulas and a unit known as molarity. Continue bringing your calculator. Consider bringing out those test-taking tool pages so you can make sure they're test-ready by next week. Alrighty. We're off to lab where we'll practice nomenclature, if you have Tuesday, that is. If you have questions, please stick around. I can answer them as needed. Well, I don't have one to print out. If you find a good image, you may certainly print one. I know that there's one on the Google slide. Yeah, that staircase. Most students like that, but you can probably find that as an image already built.